5.8 gigahertz or some other. It always has negative antiharmonicity. And that's good. That means that I can turn this into a quantum bit, because if I can apply tones to cause transitions between level 0 and level 1 of my qubit, but at some reasonable approximation, I'm off resonance in driving the 1 to 2 and other transitions, and therefore I could approximate this in some regimes as a two-level system if the antiharmonicity is big enough. Okay. So again, without going into details as to why the energy is cosine of the flux, just telling you that's the case, I can perhaps, I can't stop the expansion of the cosine of phi squared, but maybe I can stop at 5 to the 4th, which will turn out to give me this desired antiharmonicity. So, so if I were to keep going here, there would be another term with some coefficient, minus A4. Now, it turns out there's something not totally kosher about this expansion, because it fails to recognize that the physical, in this geometry, this angle phi really is an angle. The physical state of all the electrons in the superconductor is identical if you add 2 pi to that angle. It's the same state. It's not different. And so there's the wave function actually obeys periodic boundary conditions. And what I'm really doing here is cheating and saying this potential rises up so high that I could just think of the wave function as just vanishing, like a harmonic oscillator. If I were to stop the expansion of the order phi squared, the potential just keeps going up and up and up and up and up, and the wave function has to vanish as phi goes to infinity. And I fail to correctly capture what are called instanton, or some non-perturbative tunneling effects where the phase can tunnel from 0 to 2 pi to 4 pi. But it turns out in the regime that we're interested in, these are not important effects. In fact, getting rid of them gets rid of an important problem that causes dephasing in these qubits. And it's an extremely good approximation to make this expansion of the cosine. It turns out, somewhat paradoxically, that the expansion of the cosine gets better and better the larger is this coefficient. You normally think, if I'm going to expand this, probably I'm making an error unless this is really small. But it turns out you want this really big, because the 0-point fluctuations of phi can get smaller the bigger this is. The more powerful is the, so this is a quantum rotor, right? This is angular momentum. This is the gravitational potential of a quantum rotor. And the stronger is gravity, the steeper is this potential, the more you're staying with very small 0-point fluctuations near the bottom. And the less likely some tunneling event where you go all the way around like this, that becomes exponentially unlikely. So there's some subtleties there for theorists, but have time. In the right parameter regime, they're irrelevant experiments. Okay? But we know, so this phi squared term is going to give us our regular harmonic normal mode, and then this is going to give us the anharmonicity, and it's going to have some form like that. And there are going to be all kinds of terms like A dagger, which strongly fail to commute with the quadratic part of the Hamiltonian. They mix level 0 and level 4. So you can, at some, we don't do this when we do our numerics, but just for understanding what's going on, you can make a rotating wave approximation. And keep only the terms that aren't rapidly rotating. They have normal order. They just have some form minus alpha A dagger, which you can work out. The nice thing about this form, because it commutes with the original Hamiltonian, it's diagonal in the same basis. So the wave functions for these guys are just the Hermite polynomials times the Gauss. It's the same wave functions. They just have slightly different energy levels. So 0 to 1 is still h bar omega, but 1 to 2, if I define this to be alpha over 2, then alpha in this case would be the alpha would be the 200 megahertz negative anharmonicity. Is that clear? Okay, so that's there are many other kinds of superconducting qubits. They have different things, types of noise they're sensitive to, different pluses and minuses. This one's the simplest to build and holds the current world record for phase coherence time, which I'll show you tomorrow. So now we want to couple, if we want to think about like the James-Cummings model, where you have an atom in a cavity. Did that get covered already or something? Okay. We'd like to make contact with that world as electrical engineers. So how do we do that? So imagine that I have one of these little qubits, and it's connected, it's inside a cavity. The cavity has multiple modes, or it's part of an electrical circuit. It's some kind of Josephson junction, some capacitive coupling to a lumped element resonator through some coupling capacitor like that. There's some way that my atom is coupled to the outside world. How do I deal with that? Well, it turns out that there's a general formulation of how to do this as an electrical engineer that we just published recently. In which you imagine that I have a box. I buy some commercial Maxwell equation solver that knows how to deal with superconducting walls and little pieces of superconducting metal here and little feed lines, all kinds of things in tremendous detail by filling space with 200,000 finite element points, solving for the normal modes of this thing. And roughly speaking, what we do is solve for the normal mode frequencies and their characteristic impedances of the resonances, and then we use that information to just quantize everything and throw in the effect of anharmonic terms from the one or more Josephson junctions that are present. So if I were to sit at this point and let's say approximate the Josephson junction, either remove it or approximate it as an inductor, then I have a linear circuit, and I could ask, what is the admittance of that circuit? How much current flows when I apply a voltage? That's a simple thing that this numerical code can define. And it's purely imaginary because there's no resistors anywhere, if you're careful. And there's a series of zeros of the admittance. And the zeros of the admittance for a parallel circuit, they tell you the normal mode frequency. And the slope of that zero, the line tells you the characteristic impedance. It's 2 over z. Now, some of these modes are qubit-like, some are cavity-like. It's fine. And knowing the frequencies at which these occur and those slopes and the relationship between the 0-point motion of the flux for each of those modes at this point can be determined. In other words, I can get an expression for the flux operator where my Josephson junction is going to be in terms of some the flux operator for each of those normal modes weighted by how big the amplitude of the normal mode is at that point in my circuit. Like there could be a mode way over here which is not much coupled, could be strongly coupled. So I can just numerically find those things. It's just the generalization to multiple modes of the LC exercise I went through here. And then I can now put in the fact that I don't actually have a linear circuit, I have a Josephson junction here. And there's going to be a term, let's say, that I could stop the expansion at 5 to the 4th. And again, numerically, we don't do that, but just for purposes of illustration. And I'm going to end up with all kinds of terms, but they're going to be interesting terms like this. I'm not, again, making rotating wave approximations. Where each mode is going to become slightly anharmonic. Every mode will inherit anharmonicity from the Josephson junction. The most anharmonic mode we'll call the qubit. I mean, this is sort of agnostic as to what. They'll all start out as harmonic oscillators. And then the lesser anharmonic things we'll call modes of the cavity. And then, in addition to these sort of self-Kerr photons, modes interacting with the themselves. There are non-rotating terms called cross-curve, where there's a term in the energy that's the number of quantities in mode 1 times the number of quantities in mode 2. So if mode 1 is, let's say, the qubit, we've decided it's the most anharmonic thing. And for various reasons, we believe we can only need to deal with the lowest two levels of the qubit. That is to say, A dagger 1 A1 is either 0 excitations or 1 excitation. Then I can replace this now I'm going to go from assuming the qubit is weakly anharmonic to some strongly anharmonic, but I somehow only need to deal with occupations number 0 and 1, then I can make a pseudo-spin, and 1 plus sigma z over 2 is either 0 or 1. And so I end up not directly here with the James-Cummings model, but the dispersive approximation to the James-Cummings model when the qubit is, the atom is detuned from the cavity. Again, I don't know whether this was covered, but the qubit and the atom, the qubit and the cavity have different frequencies, so the atom can't actually absorb a photon from the cavity, but it can virtually absorb it and spit it back. And the effect of that is to produce small energy shifts of the resonator frequency depending on the state of the qubit. And that's going to be the central little Hamiltonian of my next talk, where through the miracle of being able to, I mean, imagine the transition dipole of this atom. It's 3 or 4 Cooper pairs moving a millimeter. So, you know, it's big compared to, you know, optical transitions in atoms, and it's even big compared to the Rydberg atom transitions that Serge Haroche uses. So it's really gigantic. And as a result, the coefficient here, the dispersive coefficient that tells you when I flip the state of the qubit, how much does the cavity frequency move, can move 10,000 light lengths. And so we're going to use that extreme strong dispersive coupling tomorrow to show you the world's largest Schrodinger cat. Okay, I'll stop there.
Thank you. Okay, so let's continue. So next lecture will be Girvin, second lecture on circuit PD.
Okay, thank you. I'm going to tell you about experiments in a group of particularly my colleague Rob Sholkoff, and based on some theoretical ideas. These guys, this is a somewhat, I now realize, incomplete list of alumni because I don't see John's name here. So the first part of the talk will just be kind of a review quickly of the things I talked about last time. So quantum electrodynamics is the study of the quantum fluctuations of the electromagnetic field that it has on atoms and electrons. It changes the mass of particles, it shifts energy levels, it causes spontaneous decay of excited states of atoms by photon emission. So in hydrogen, T1 time is only about a nanosecond. In the qubits that I showed you last time, if they were not in a cavity but in free space, they would have a spontaneous emission lifetime of between 10 and 100 nanoseconds. And one of the interesting things about cavity QED is you can modify the spectrum of the electromagnetic field and therefore of its fluctuations by putting the system in a box that has discrete photon modes of different frequencies, and you can make them the same as or different from the transition frequencies of the atoms. You can engineer the quantum fluctuations of the atoms. And so we're going to try to do the analog of that in cavity QED with circuit QED. And so it's going to be microwave photons inside superconducting circuits or superconducting cavities, artificial atoms like the one I talked about last time based on Josephson junctions. And as I hinted at the end of the last talk, there's extremely strong coupling between the photons and the atoms because the transition dipole moment is several Cooper pairs moving a millimeter. You can get gigantic direct coupling, or in the dispersive limit where the qubit is detuned in the cavity, you can get gigantic dispersive second order coupling. So you can do nonlinear quantum optics in a totally new regime of ultra-strong coupling where things become extremely nonlinear even at the level of single photons. You can put one photon in the cavity and be unable to put the second photon in because they would interact so strong. And this is to be contrasted with most situations in regular nonlinear quantum optics or lasers and materials where it's difficult to get the medium to be sufficiently nonlinear. So we talked about building LC resonators, avoiding resistors to give it a dissipation, adding Josephson junctions so that we get something with an anharmonic level spacing so we don't just have a harmonic oscillator. And we'll use the two lowest levels as the levels of our artificial atom. So, we're trying to build the equivalent of a hydrogen atom or something with a simple spectrum, and roughly speaking, we're building LC oscillators, possibly slightly nonlinear because of the Josephson junction. And I didn't talk about it last time, but think about the amazing fact that this circuit contains, and they keep getting bigger, so I haven't calculated the number recently, but let's say 10 to the 13 electrons. And yet, it has a spectrum that's as simple or perhaps simpler than hydrogen. It effectively has just 1 degree of freedom, which is the uniform sloshing of the charge back and forth. I kind of glossed over that last time, but the origin of that is twofold. One, the superconducting excitation gap. You have to, if the Cooper pairs don't move coherently, it takes a finite energy to break apart the Cooper pairs. But second is the extremely strong repulsion, Coulomb repulsion, which forces the electrons to all move together. If they moved in opposite directions, charge would build up someplace other than on the capacitor plates, and you would have an extremely high energy plasma excitation instead of a low frequency qubit oscillation. So there are two reasons that most of the degrees of freedom are gapped out: the superconducting gap and the long-range Coulomb force. So as long as these objects are physically smaller than the wavelength of light at their transition frequency, they basically have just 1 degree of freedom. And I showed you this simple transmon qubit last time. It's some kind of antenna, 2 halves connected by a Josephson junction. Here's an actual picture of the millimeter-long antenna, little sub-micron scale Josephson junction connecting the 2 sides. And here's the large transition dipole moment, which leads to the coupling G. It's sort of related to the little g that Ash has been talking about. The transition dipole moment times the root mean square 0-point fluctuations of the electric field in the cavity divided by Planck's constant. That's this coupling in the James-Cummings model, and it can be 100 or 200 megahertz without difficulty, which turns out to be big. So this guy is sitting evaporated on a sapphire substrate, hopefully low dielectric loss, and the sapphire substrate is sandwiched inside 2 halves of an aluminum box forming a cavity. There's an input line and an output line for sending signals either at the qubit transition frequency to put the qubit somewhere on the Bloch sphere, like an MMR, rotate it around, or send photons near the cavity frequency, which you can use to read out the state of the qubit. There are also experiments now underway with two separate cavities connected by what's called a vertical transpond. One cavity can be high Q so that you can store interesting photon states in it. The other can be low Q so that you can rapidly read out the state of the qubit. Or, as you'll recall, I told you that all the modes inherit nonlinearity, and one of the terms they inherit is a cross-Kerr term, where the energy is proportional to the product of the number of photons in this cavity and that cavity. And so a photon present in this cavity shifts the frequency of this cavity, and you can use that to read out in a non-destructive way the number of photons in that cavity. This is not absorbing the photons, this commutes with photon number in cavity 1. So it's a Q and D measurement. Can be used for a Q and D measurement of the photons. So, as I mentioned, we're trying to do the sort of moral equivalent of NMR, a single nuclear spin, which is quite difficult. But easier here because we're not using the tiny magnetic moment of a nucleus, we're using the giant electric dipole moment of a pseudo spin, an artificial atom with 2 levels. And we can apply tones which tipping pulses, we can move the fake spin around the black sphere, and we can also read out the orientation of that spin. So here, for example, one applies a pi pulse, which moves the qubit from the ground state to the excited state. Then you wait, and then you apply a tone at the cavity frequency. I'll explain how the readout works in a second. And you see whether the qubit is still in the excited state. Sometimes it is, sometimes it isn't. The average probability of being in the excited state decays exponentially with a characteristic time t1, which these days can be as large as 100 microseconds. But we want to be atomic physicists. We want to do Ramsey fringe experiments. We want to make a coherent superposition of ground and excited state and see how long the phase of that superposition survives. That's not the same thing as how long the energy in the excited state survives. And so you make a pi/2 pulse, you wait, you make another pi/2 pulse, and you see whether the qubit is in the excited state, possibly throwing in a pi pulse in the middle to echo away some motion noise. And you can get phase coherence times of order 150 microseconds, which is the current world record for superconducting qubits. So when all this started in 1999, the Nakamura and the NEC group built the first superconducting qubit. It had an immeasurably small coherence time, sub-nanoseconds perhaps, and it's gone up pretty much exponentially over a factor of 150,000 roughly in the last 14 years. So each order of magnitude is harder than the last one. Each order of magnitude was achieved by some clever redesign of the cavity or the circuit or the qubit. But so far there's no evidence that we've reached any intrinsic limits. But as I said, the next order of magnitude is always harder than the last one. But this is real Moore's law plot. We don't have a Moore's law plot for the number of qubits yet. We're still doing 1, 2, 4. But there's no point in trying to scale up to large numbers until you have large coherence times. So we're getting there now. And basically, you can now say that, at least for small quantum computers, it won't be the decoherence that. Okay, so I'm going to talk about this extreme quantum optics rather than quantum computing, and this extremely strong dispersive coupling that can occur between the qubit and the cavity, and show you how you can very easily make Schrodinger Cat states on demand. And then these guys have some amazing ideas for encoding the state of the qubit into the continuous quantum variables of the cavity in the form of two different cats corresponding to the up and down parts of the qubit wave function. And that can actually be used to do make an error-correctable memory. That even if the cavity loses some photons, you don't lose all the information about the qubit space. It's a totally amazing idea. And the experiments have realized kind of the first step in the protocol. There are many subsequent steps, but they're, this has some chance of actually working. And then my postdoc, Simone Mead, has extended these ideas to think about how to do stabilizer pumping for the various topological quantum error correction codes. Again, an idea that's, it's theorist ideas, but it's not totally off the real axis. Okay, so I want to show you the kind of toolbox that we have available due to the strong dispersive coupling of the atoms to the cavity. The cavity is, the qubit is detuned from the cavity, so the qubit can't absorb photons except virtually and then re-emit them. And as I indicated to you last time, that leads to this dispersive coupling. So let's back up. So here's the harmonic oscillator, which is the resonator. Here's the two-level pseudo-spin of the qubit. There's some damping terms that we wish were zero but aren't. And these two frequencies are quite different from each other. And as a result of everybody inheriting nonlinearity from the Josephson junction, there's a kind of cross-Kerr term in which the coefficient of A dagger A, which is the cavity frequency, now depends on the state of the qubit. There are two different cavity frequencies depending on whether the qubit is up or down, and they're split by 2 chi. And if chi is small compared to what? Compared to the cavity line width kappa, then there's a small frequency shift, but there's a phase shift, as Ash showed us. And you can use the phase shift of photons transmitted at the cavity resonance to determine the state of the qubit. So that's how the readout works. But I'm going to be talking here about a limit where this chi is much, much, much bigger than the cavity line width, which we'll call the strong dispersive regime. So even this chi is, roughly speaking, that little g squared divided by the detuning of the qubit in the cavity. So the coupling is so strong that even the second order effects of the virtual coupling are bigger than the damping. So, as I said, there are two different resonance frequencies of the cavity, omega r plus chi and minus chi, depending whether the qubit is in the ground state or the excited state, and they're separated by possibly thousands of line widths. Any questions about that? So you could, shine microwaves on the cavity and figure out what frequency it resonates at and quickly determine the state of the qubit, for example. But there are other things you can do. So, for example, I could shine microwaves at this frequency, which is on resonance with the cavity, if and only if the qubit is in the ground state. And it's totally off resonance by thousands of line widths if the qubit is in the excited state. So I will if I shine microwaves on the cavity, I will displace it. I will produce a coherent displacement. If and only if the qubit is in the ground state. So I'll call that operation dg sub alpha. I'll produce a coherent state labeled by a complex number alpha, which is, x1 plus x plus iy, the two quadrature amplitudes that Ash has been So it's a conditional displacement of the cavity. So this is a very, very powerful new element in the quantum engineer's toolbox. And of course, you can do the same thing with frequencies over here, displacing the cavity only if it's in the excited state. So that's tool number one. So just to show you what it can do, suppose I'm in the ground state of the qubit and the vacuum state of the cavity, and I apply this conditional displacement, then the qubit is still in the ground state because I'm applying a tone to the cavity, not to the qubit. But I displace the cavity because it's on resonance. So I get, I'm calling I and Q, that's X and Y, or X1 and X2, in various notations in Keith's talk. But this phasor arrow represents the size and phase of the coherent state that is produced. On the other hand, if the qubit were in the excited state, this will do nothing because the cavity is completely off resonance, so I'll end up with qubit in the excited state, cavity still in the vacuum. That seems straightforward enough. But what would happen if I did a pi/2 rotation on the qubit, so it's both ground and excited state at the same time? Then I'm going to get this weird entangled state where the qubit is in the ground state and the cavity is full of photons. And the qubit is in the excited state and the cavity is in the vacuum state. So I get this strong entanglement between the qubit and the state of the cavity. And it's possible to do this in such a way that this state contains on average 100 photons. This one is still 0. So it's a huge, almost macroscopic entanglement of this with that. And this is what is an actual Schrodinger cat. Now, we're going to be talking about photon-only Schrodinger cats, which is kind of a common use of language in the field, but it's not really right. This is a real Schrodinger cat in which the cat is dead, qubits in the ground state, and the poison bottle is open, the cavity is full of photons. Coherently superposed with the cat is alive, and the cavity is empty, the poison bottle hasn't been broken. Okay, that's a real Schrodinger cat state. And you can undo it by appropriate conditional displacements and save the cat. It really is in a superposition of dead and alive. Okay, so this toolbox, conditional displacement of the cavity. This tool permits entanglement of the qubit and the cavity in the manner described. And now I'm going to, that's tool number one. Now tool number two, again using this dispersive Hamiltonian, is going to be a conditional flip of the qubit if and only if there are exactly n photons in the cavity. And we achieve that with the very same term by reinterpreting this dispersive term. It's not that the coefficient of A dagger A, which we call the cavity frequency, now depends on sigma z, but through complex theoretical manipulation of parentheses, I can say, oh, no, it's the coefficient of sigma z that depends on how many photons are in the cavity. And the coefficient of sigma z is the qubit frequency. So the qubit frequency is going to be the bare value plus 2 chi times the number of photons. So there's a quantized light shift of the qubit transition frequency. If I send in a photon at the qubit frequency, I have to do more work or less work, depending on the sign of chi, to flip the qubit, depending on how many photons are in the cavity. And because chi is not only thousands of cavity line widths, but thousands of qubit line widths, it's very easy to resolve these individual transitions. So here's some data. This is the absorption spectrum of the qubit. How do we do that? We shine light at this frequency, 7.45 gigahertz. We try to flip the qubit, then we read it out and see if it did flip. And that's the absorption spectrum. And you see peaks corresponding, chi is negative, so the frequency jumps down by 2 chi. When there are 0, 1, 2, 3, 4, 5, 6, 7, maybe 8 photons in the cavity. This data was taken over a long time, steadily pumping the cavity, so it's in a coherent state roughly. And this is the time average of the number of different photons, and you see roughly the Poisson distribution that you expect for a coherent state. And I told you this splitting was thousands of line widths. It doesn't really look like that here, and the reason is that this is power brought by roughly a factor of 100. But they're perfectly well resolved, so I hope you're now convinced that microwaves, despite their name, are particles. Right? The number of particles in the cavity is an integer each time I measure it. Measuring the number operator, it has integer eigenvalues. I always get one of the eigenvalues. Okay, so we call that number splitting. So now how can I make an interesting tool out of that? Well, suppose that I apply a pi pulse to the qubit at this frequency, which lies right on top of this peak. But that's the transition frequency if and only if there's exactly one photon in the cavity. So I will get a conditional bit flip, pi sub n, in this case n is 1. That I flip the qubit if and only if there's exactly one photon in the cavity. So now I can get all kinds of weird entangled states. I can choose pi 0, pi 1, pi 2. I have all kinds of new tools in my toolbox. Okay, questions about that? Okay, so now we want to combine the two tools, namely conditional flip of the qubit if and only if there's n photons in the cavity, and conditional displacement of the cavity by a distance alpha if and only if the qubit is in the ground state or it turns out you can use this to do multi-qubit geometric entangling phase gates. I have a paper in preparation on that. And what I'm going to talk about is now how easy it is to make gigantic Schrodinger cats. And so these guys are the main experimental driving force, and these guys have been the main theoretical driving force. So what we'd like to do is map a qubit superposition onto what's called a pure photon cat state. That is a superposition of coherent state alpha and minus alpha. So the phasor is here or the phasor is there. And there's another phase, namely the phase of the superposition of those two things. Don't get confused, there's a lot of phases around. There's the phase of the coherent state, this angle, and there's the phase of the superposition here, which is that guy, which we'd like to faithfully get from the qubit. So I showed you a real Schrodinger cat before where the qubit was entangled with the cavity. Now I want to use these two tool sets to produce this so-called photon cat state. So first I'll see if I got to tell you how I do it. I guess I'm not going to tell you how I do it. So let me quickly outline how we do it. So we entangle the qubit with the displaced cavity. So the qubit's in the ground state, cavity heavily displaced. qubit in the excited state cavity in the vacuum. Okay? And now, if then the qubit is entangled with the cavity, but now one of the cavity states has no photons in it. So I can apply a conditional pi pulse on the qubit that only works for the component of the cat that has no photons in the cavity. And then I've unentangled the qubit from the cavity, and then I can take these two blobs and slide them back so they're symmetrically placed like this and produce this state. I can go through the details. I'll try that afterwards. I don't think I have a slide. So here is what's called an even cat. I have a plus sign in the superposition between amplitude beta and minus beta. So think of the coherent state of a harmonic oscillator might just be a Gaussian displaced over to the right. Now we have a superposition of Gaussian here and Gaussian there. That wave function, that first quantized wave function, is symmetric in the coordinate, and so it only contains even numbers of photons. And we do our photon splitting experiment. We measure the spectrum of the qubit, and we see big peaks when there are even photon numbers, and very small peaks when there are odd photon numbers. So that's a hint that it's working and that this plus sign is well defined. Now, you see a lot of kind of wiggles in the data there. That's an unfortunate coincidence from a commensuration in the duration of the pi pulse that's used to try to flip the qubit and this splitting frequency. And so there's some little extra ringing here, which we regret that they haven't felt the need to retake the data. But anyway, you can see a large difference between even and odd photon. This is what an odd cat looks like. You can put the qubit in a superposition of up minus down and map that minus sign onto the Schrodinger Cat superposition, and therefore it's odd and contains 1, 3, 5, 7 photons. So it seems like it's working, but what you'd really like to do is measure the Wigner function. And like all the speakers before me, I'm not actually going to tell you what the Wigner function is. It's a transformation of the density matrix into these quadrature amplitude variables, x and p, or x and y, x1, x2. And it's a kind of quasi-probability distribution. It doesn't have to be positive. In fact, for non-classical states, it's negative. But roughly speaking, it tells you the bigger it is at different points in the IQ phase space, the more probable it is that if you were to measure where you are in IQ space, you would find the system there. Now, since I and Q, the two quadratures, are non-commuting, they're incompatible observables, you can't measure them both perfectly. So there's a certain fuzziness to this. Okay. So here is a picture of a Schrodinger cat, and this blob over here, here's the origin in IQ space, and the phasor that's sitting here, that's the beta, and there's the minus beta, or alpha, I guess I call it here. The mean number of photons in the coherent state, alpha squared, is 7, which might not be a world record. It's comparable to the biggest ones, I think, that the Paris group has created. And but you could have an incoherent mixture of those two coherent states, and how would you tell? Well, the nice thing about the Wigner function is that right in the middle, you see these rapidly oscillating interference fringes, and they turn out to be precisely, as you go along here, this momentum axis, trying to get to the coordinate, that's actually the two-slit interference pattern from these two slits. And the fuzziness the blob, the fuzziness you see here, it's not a point like a classical phasor. That's the fact that I and Q don't commute. This is vacuum noise. You're looking directly, these are really precise measurements and directly showing your vacuum noise. And you see the colors here, red, blue. So the blue is negative. The Wigner function is going negative in the middle, indicating that this is indeed a non-classical state with a and the phase of these oscillations is intimately related to the phase of this superposition of those two blobs. Now, Schrodinger cats are famous for being very delicate. If you were to lose a single photon from the sky, you would change the parity, right, from even to odd. And you would change the phase. You would flip blue and red here in this interference pattern. And this is the bigger the cat is, the faster you tend to lose photons from the cavity. And the faster you flip the phase of these interference measures, and they wash out. So the fact that you can see these oscillations, that's the ironclad proof that you really have a well-defined phase of the superposition of these two relatively macroscopic coherent states, alpha and minus. Okay. Now you can also superpose three different coherent states, get some weird three-slit interference patterns by similar tricks. And you can do four-legged cats, in which you see in the center that the fringes have fringes. And these are, very rapid fringe variations, small on the scale of the zero-point uncertainty of the vacuum noise. And again, that's why these are such delicate objects that quickly become classical when they become very large. But for n bar equals 7, you can do this well enough to see those fringes. And it turns out that making this four-legged cat is the first step in this protocol that Marihimi and Laktas figured out for robustly storing the qubit state in the cavity in a way that can survive photon loss. Because when you lose a photon, you change the parity of this guy and that guy. And there's a way to figure out what happened. Of course, we should make the Yale cat with this particular superposition of three things. It's not that good yet, but we're working on it. So now I'm going to show you a cut down through the center for a two-legged cat of these interference fringes. Because when you make the cats bigger than this, it's just technically difficult to reconstruct the entire Wigner function. It's too much. It takes too much time for one thing. But you can make a cut down through here and see the well-defined phase of those oscillations and the fact that they're going negative. So here's beta equals 2 or alpha equals 2, so there's 4 photons on average. There you see the interference fringes going back and forth. Here's 7 photons. Here's 10 photons. And here's my favorite, 25 photons. You can see the fringes going faster and faster and faster because the two slits are getting further and further apart, so to speak. And this is becoming more and more delicate, more, losing photons faster and faster and washing out these faster and faster fringes faster and faster. But, and at an intermediate step in the production of this pure photon cat state, there was the true Schrodinger cat state with the entangled qubit in the cavity, in which the qubit was entangled. 2 states of the qubit corresponded to either 0 photons in the cavity or 100. And then when you displace that thing back halfway, it falls down to by factor 4 to 25 photons. So I haven't checked, but I think this is probably the most macroscopic superposition, coherent superposition that's ever been produced. And there's no evidence that quantum mechanics is failing. Okay, so as I mentioned, once you have these four-legged cats, which are superpositions of four different coherent states, it's possible to make a quantum error correctable memory that survives photon loss. I won't go into those details, but refer you to these two preprints, which are pretty remarkable. It assumes the only error is photon loss, that the cavity doesn't have any intrinsic dephasing, which we don't know for sure yet, but that's an assumption. It's also possible, as I mentioned, to extend these ideas to many qubits in a cavity with one mode, and if you allow me the fine-tuning of having the dispersive coupling be the same for this array of qubits, then it turns out it's possible to measure and pump to the correct values the four-spin stabilizer operators that define the toric or surface code of ITAMP, and produce a topologically protected set of quantum bits. And what's amazing about this protocol, I mean, the toric code requires the qubits to be laid out in a torus or a multi-handled torus, depending on how many qubits you want to store. And it's actually possible, in principle, with this Hamiltonian, you don't have to physically lay out the qubits in any particular place, but mathematically, by choosing what you measure, who is defined to be a neighbor of whom, you can define the topology and reconfigure the topology of the manifold that the qubits are living in at will. So it's, in that sense, a little more realistic than people that want to try to actually build toruses. So I'm not going to go into any of the details. It's in this preprint, but it involves doing kind of forming a Schrodinger Cat kind of picture in which basically the time evolution of this, e to the I, this thing times time, if you choose the time correctly to be pi over pi, you end up with a product of the sigma z's as the effective time evolution operator. And if you do it halfway and then flip all the qubits that you don't want to contribute to this thing and then do the rest, you can pick out any subset of the qubits and find their either z parity or their x parity. Any subset, they don't have to be neighbors, just any number. Easiest to think about is 4. So it's kind of still far from being realized experimentally, but it's an interesting possibility that I think is a lot simpler than some of the other ideas, perhaps, for realizing the toric. So in summary, we have this incredibly simple Hamiltonian, but because of the gigantic coupling strength compared to the dissipations, we have now all kinds of tools for conditionally manipulating the quantum state of the cavity or the qubit or entangling them in a way that allows us to make exotic quantum states like Schrodinger Cats and map between qubit states and the continuous quantum variable states of the cavity, where there are enough degrees of freedom that you can actually do perhaps do quantum error correction, and perhaps even do topological quantum computation. So that's the end of the story, and I'm happy to take questions.